Hello everybody, welcome to my video on quantum entanglement. Today I'm going to be discussing quantum entanglement, quantum computing, quantum cryptography, quantum teleportation, what happens when we look at entangled particles, and how do we produce entangled particles. So let's begin. So let's say we have two tennis balls, tennis ball A and B, and we're located in Wimbledon, the tennis stadium. Now entanglement is a link between two particles, and you can't observe this link. If you observe it, it ceases to exist, and it's due to something called superposition, and the two particles or two tennis balls will be in two different types of spin. And let's say we move tennis ball A up into the crowd, tennis ball B will also move up by the same displacement into the crowd. So that shows that distance really doesn't matter for quantum entanglement. So another example I can show you is if tennis ball A is in England, tennis ball B is in Madagascar. If we move tennis ball A, it'll be somewhere in Iceland, and tennis ball B will be somewhere in Kenya. So it really shows that this picture could be a picture of the universe. The size doesn't matter, and that's one of the cool things about quantum entanglement. So what happens when you observe entanglement? And there's a famous experiment known as Schrodinger's cat, and what we need is a box, a cat, a vial of poison, and a radioactive detector. And what we need to do is we need to put all three things into the box, and let's have a look. And here we have a radioactive detector inside the box, and that detector will detect one radioactive decay, and it could happen at any time whatsoever. And once that radioactive decay happens, it will fire, causing the hammer to break the vial of poison, killing the cat. So if we stood outside the box, you wouldn't know if the cat is dead or alive, long as it didn't move, and you couldn't see any movement of the cat in there. And it could be said that it's in both states, and this is known as superposition. It's in two states at the same time. The wave function also could be said. So here's a picture. The cat is alive, but it's also saying it's dead. If I put a 50p in there, it could be heads or tails. It's 50-50 chance, and that's known as superposition. So that's what happens, and as soon as you open the box, you will determine, let's say if the cat is dead, you then know that the cat is not alive and that it's dead. So once you observe it, you change the link between the particles. So how do we produce entangled particles? So what we need to use is something called an SPDC laser, known as a spontaneous parametric down conversion laser. And what you do is you fire photons into a nonlinear crystal, and they have a 1 in 1 billionth chance of splitting in half. Energy is conserved in this splitting, and here they are, the split. So the energy of these two was the same as the previous one that was fired from the laser, and they'll go down the wire and can be used for experiments. It's a very inefficient process, and here's a quick summary of entanglement. It's got lots of applications in the real day, lots of proof of theories, and it's well funded, $200 million in the US alone. High equipment costs, £30,000 for that laser, and high research and labour costs. So I'm going to now talk about computers. Now computers work on a binary system of zeros and ones, and if you look to each 0 or 1, you could call that a bit of information, and that works in the processor, the CPU, and that's the basics of computers that we need to know. Now a quantum computer is rather different. A quantum computer uses zeros and ones at the same time, like a mixed state, the same as the particles. And the cool thing about that is it really does increase the power of the computer and the amount of calculations it can do per second. Here is a picture of a quantum computer. It shows how big it is. They're very expensive. They cost around £10 million to buy by D-Wave. And to exhibit the powerfulness of a quantum computer, I'm going to show you this. And let's say this is position A and this is position B, and we want to travel from A to B. Now a regular computer would go down every single road and work out the length, and it could calculate it and say take about a minute. Now a quantum computer will work it out all at the same time. It'll calculate them all very quickly, and then it can produce the number rather rapidly. But let's say we added a road from here to here. A normal computer would have to work out the whole thing again. A quantum computer would use another quicker algorithm, and it would be able to use that rather efficiently. The only problem with quantum computers, other than its expensiveness, is something called decoherence, and that is any type of radiation that affects the entangled particles in the quantum computer. That can be such as vibrations, kinetic energy, electromagnetic, cosmic background radiation, movement, any type of radiation, because these need to be kept at close to minus 273, so absolute zero. So quantum cryptography. So here's David Cameron and Angela Merkel, and they're on the phone together, and David Cameron's sending information to Angela Merkel. Now, a cool thing about quantum cryptography is we can stop hackers getting our information. So let's say we bring in two hackers from the News of the World. David Cameron is sending his information, but it's getting hacked by the News of the World hackers. Once you observe the information, it changes the state of the information, same as I said before. So once you send that particle to Angela Merkel, she will be able to detect the change in that quantum information, and that makes them angry. So that's a bad thing about cryptography, but we can change it now, so that's cool. So here are the advantages and disadvantages. If it's hacked, the receiver can tell that it's being tampered. It increases national security, such as WikiLeaks. Only problems, it's got a very short distance, around 36 centimeters, and it's rather expensive. Quantum teleportation, rather interesting. So let's say we have an office, two teleporters in a place, and here's a teacher who I know, and what he wants to do is go to Hawaii on holiday. So the person runs into teleporter A, and he has to destroy himself, and that will then turn him into information. The information then can be sent from one teleporter to the next teleporter via wired connection. Then that information can then be resynthesized to form in the teacher again, who will then be in Hawaii. So there's the premises of quantum teleportation. It's not a Star Trek thing, this is real life teleportation. So what are the problems with teleportation? You have to destroy the object you're teleporting, which brings up ethical issues about if you have a soul, would you destroy it and release your soul? So would it be a clone of the teacher? Many religious groups would consider this murder, and the technology isn't currently advanced for this stuff. Finally, what is the future of teleportation? At the moment we can do atoms, in around 10 years we can do cells, in around 100 to 200 years we can do humans, and that is predicted by Michio Kaku. If you've got any questions, please leave them in the comments below, and thank you for watching.